All right, today we're looking at internal and external differentiations of the postsynaptic membrane at the neuromuscular junction. And this was done by Nobutake Hirokawa and John E. Husserl in 1981. So their objective is they wanted to determine how the clusters of receptors that are found on the postsynaptic membrane are immobilized there. And this was important to them because they had noticed, because they had, first of all, they had found these clusters there. And it was important to them because they had noticed that there was always constant turnover within these clusters, but the receptors themselves were not moving, they were staying immobile. So that was very interesting. They wanted to try and figure out why that was. So some background information, first of all, is that the neuromuscular junction, NMJ, represents the area between the end of a motor nerve and the muscle. And the muscle could be anything. It could be a smooth muscle, a bone muscle, cardiac, whatever it might be. And the postsynaptic membrane, PSM, is the membrane that's receiving the signal. So in other words, this is the membrane that's actually on the muscle itself. So the signal would come through the motor nerve and go to the muscle, and the membrane on the muscle is what would be the PSM, or postsynaptic membrane. And they had noticed, like I mentioned earlier, that on the PSM they had found that there were these clusters of receptors that were being held in place, despite the fact there was constant turnover of individual molecules within these clusters, which is very weird, which is why they want to try and figure out why this was. So they used a model system on something they called the torpedo electric organ, which is essentially an organ that comes from an electric stingray. And they were using this new and improved method on it. And the reason why they had to use a new method is because, as I mentioned here, there's previous methods that people had tried to use: freeze fracture, negative staining, and high voltage electron microscopy. And unfortunately, they could get you decent images, but unfortunately, none of them in and of themselves could give you a good sound infrastructure image, which was the problem. So what they ended up using is they used this new method on the rat, snake, and frog, NMJ. And part of this method was they had to denerve some of the muscles, which is just simply cutting the muscles, the nerves, cutting the nerves so the nerves are no longer connected to the muscles. And one other thing to note here is that you're going to see these freeze fracture, negative staining stuff again. It's just that they're going to be used sort of like succession with each other, with one more improved thing that we're going to get to. So the methods, how did they do this? So overall in the methods, they had this overall method that they used. So they would isolate the muscle, and then they would treat the muscle with a bunch of different solutions for a bunch of different times and everything like that. But the main thing is that the muscles were incubated in something called collagenase, which would be, of course, be an enzyme that would break down collagen. And we know that collagen is a key enzyme in the basal lamina surface. So what this is actually doing is it's breaking down the basal lamina surface, which is the main improvement in their new method. Because if they realize if they get rid of the basal lamina, they can actually get a better view of the infrastructure of the PSM. And so they had isolated the cutaneous pectoris muscles from the frog. And they had essentially like two samples mainly. They had the one where they just treated with the solutions and incubated collagenase, treated more solutions. And they had a second one where they had denerved it for 2 weeks, and then they treated it in the same format. Then they had ventral costocutaneous muscles from a common garter snake. And it was treated, they only had one section of this, and it was treated in the exact same way as the frog was. And then they had used diaphragm muscles from the rat. The thing is, so these diaphragm muscles weren't exactly what they wanted. So what they had to do first is they first had dissected them up into smaller pieces, and then they homogenized them using yet another solution, and then they had centrifuged it down, and then they took that sample and treated it in the exact same manner as the original frog was treated. And the sample, and after this part, they were either going to freeze them right away, or they'd be treated with ethanol and then frozen. And then, so more methodology they would use. So essentially, after they would frozen it, they would essentially have to go through processes of either freeze fracturing, or they would just like have to heat it and do other things to it. So actually, after all the freezing processes and everything, they would get to where they would, some of the muscles, they'd cut them into thin sheets, and then they would be stained with uranyl acetate and lead citrate. I had some that were freeze fractured, etched, and then rotary replicated with platinum and carbon. And after they had done all of those things, what they had done is they finally were able to look at the sections from the staining and the replicas from the freeze fracturing and etching, and they were able to examine them under an 80 kilovolt electron microscope. And so now we're going to get into the results, and I apologize if you're a bit confused by the results. It's just that they have so many different figures that it would take too long to kind of go through and explain every figure individually. So I'm mainly just going to say what's in each figure, and that's pretty much about it. So the first three figures here. So in figure 1, it's showing a frog NMJ of the basal lamina surface. And it was mainly trying to show you, was showing the contours of like the surface, how like the rough contours smooth, that's what's trying to show you, the curves and everything. And this was done, they did a quick freeze of it, and then they had freeze substituted it, which are again some of the frozen methods I mentioned earlier. And then figure 2 is showing the exact same image, but they used a different technique to do so. And they had this one was a deep where they quickly froze, they fractured it, and then they did a deep etching of it. So 1 and 2 were just something meant for comparison purposes, and that's it. And then figure 3 is showing a frog NMJ folds of the PSM without the basal lamina. So the key thing to note here is that I mentioned that they'd be treated with collagenase earlier, which was breaking down the basal lamina surface. So the key thing to note here is that figures 1 and 2 are showing the frog with the basal lamina. So those two are showing you what you would get if you weren't using their method, which is the important part here. And figure 3 is showing the folds and the connections between the pre and post synaptic membranes with the basal lamina being gone. So the next figures they have, figures 4, 5, and 6. Figure 4 is showing the snake muscles with an oblique fracture through the muscle, which doesn't make much sense, but the important takeaway here is if you look where the arrows are on figure 4, it's showing where the surfaces between the P and T are separated, which was the important part. Also, again, this is of the PSM, so in snakes they have 2 different surfaces, which was interesting. And then figure 5 is essentially the exact same thing as figure 3, but it's just what they just said it was a 3D view of the NMJ with 2 different I don't quite know why, but that's what that is. And then figure 6, what they called that this was the true view of the frog NMJ, which was trying to show the irregular arrangement of the receptor clusters that existed on the PSM. And then the next set of figures, figures 7 and 8. Figure 7 is showing up a close-up of the frog NMJ that had been denervated for 2 weeks. So essentially 7 is the exact same thing as 6, except 6 had been treated normally and not been denervated, while 7 had its nerves, had nerves cut, so it was no longer connected to the muscles. And then figure 8 is showing the frog NMJ that was treated with saponin before freezing. So again, treating it with saponin was one of the things that they were doing. And in this case, it was treated with saponin before it was frozen, is what figure 8 is showing. And then figure 9, the last 3 figures here, figure 9 is showing the interview. So 9 is pretty much just showing you almost the same thing as 8 is pretty much. And 9 is showing the interview of the PSM, and this one was treated with saponin during fixation, which fixation was a step they had mentioned mentioned earlier in the methods of talking about when they're treating it with different solutions. That was a fixation part I didn't mention, but again, that's when treated with saponin. And the figure 10 is showing a thin section of the PSM from the rat. That's pretty much all it really is, treated normally with the same methods I mentioned earlier. And then figure 11 is showing a deep etch view of the rat diaphragm. And this one, it was first cleared with cytoplasmic proteins before freezing and fracturing. And so these 11 figures were their main results that they'd taken away from this. And again, I'm sorry if some of this is a bit confusing. It's just that there's so much that it's too much to talk about to fully go through and explain. And plus the discussion is so much more important. So they have 2 sections of their discussion talking about the exterior of the PSM and talking about the anchors. So when on the exterior, they had noticed that there was these protrusions that were roughly 8 to 9 nanometers in length, and they were found in high concentration on the PSM of all the vertebrates of the NMJ they had observed. One thing they had noticed is that they would tend to group up in two lines side by side, which is an interesting thing. Also, one other additional factor they had noticed is that only on the apices of the postsynaptic folds were these clusters of these protrusions, which was very interesting because normally they had seen a high concentration of 2 linear lines, But in this case, they were found in clusters, which are just like the receptors. And this is also, and they had shown that the receptors have been known to aggregate at these folds. So they had believed that these protrusions had to be the heads of cholinergic receptor molecules, which is essentially just a receptor that's going to bind like acetylcholine, I believe is what it is, acetylcholine. So that's all that was. But that's what they had believed that so you had these protrusions and lines, and then they had also made these clusters, which they had believed to be receptors. But now the most important part of all this is their possible anchoring junctions. So they had discovered or talked about there was 3 possible ways that they were being anchored. One was by the lateral association of the receptors on the plane, and then what this would do is it would create a very sort of large protein, or not protein, but it would create a large aggregate. Just because of its sheer size, it would be very difficult to move, and it'll probably stay relatively immobile. Then the second one was direct or indirect attachment of receptors to extracellular structures. The third and final one was attachment of receptors to localized internal structures within the muscle fiber. So, and the note here is that all 3 of these have evidence toward this, so they couldn't, at the end of the day, when I talk about the conclusion, they couldn't really conclude which one is how they were being anchored. So the first one, the best evidence they had is that they had discovered or they had found that these protrusions were associating with one another, or their receptors were. But they also said that this could just simply be that, because they also like to form disulfide dimers, so that could be a possible reason, or that when they go from like an X junction to being an actual in a junction, that maybe they want to associate with one another. So I didn't really know, but that was one piece of evidence they did have for the first mechanism. The second mechanism has the most amount of evidence towards this. The second one they observed that the basal lamina is connected to the PSM by these many thin wisps at different places, which is very interesting because why would it be connected at a bunch of different places? That's one thing they saw. And the next one is that the basal lamina also had distinct antigens that were not found anywhere else on the muscle surface, which could mean that those potentially is where it would bind to the receptors that are on the muscle, which was a very interesting thing. And lastly, they had found that the basal lamina can cause redifferentiation of the muscle and presumably be able to recollect receptor proteins, which again is very important because if the basal lamina by itself is doing all of that, then that could potentially be the reason of how that the receptors are being held in place. And then the third and final mechanism is that they had these thin sections of PSM density, which is just the area underneath the PSM in the muscle. It shows a fine meshwork of interconnected fibers that also connect to the underside of the PSM, which again is interesting because if the underside is connecting to the PSM, then hey, it might be connecting to the receptors. So the second one is that some of the meshwork would actually, so when they homogenize it, they saw that some of the meshwork would actually still cling and stay attached to the PSM, which is important because the receptors are staying attached to the PSM, even if it's being homogenized. And they used the central nervous tissue as an example. And then lastly, the last piece of evidence was that the meshwork and clusters were still found even in denervated cells. So even like the muscle cells where you would cut the nerves, and you would have the meshwork and the clusters would still be attached to each other. They would both still be all. I shouldn't say they will be attached, but they would both still be there. And the last thing that they mentioned here is that the third mechanism is probably not likely because I had observed that the meshwork connects to the PSM at too infrequent rate. So it wouldn't be very efficient to be connecting to the PSM. And then, so what did they conclude from all of this? Well, they concluded that, first of all, that these clusters, after doing all of this that they did, is that the clusters were held in place by one of these 3 mechanisms. But they had obviously said that a third one on its own is probably unlikely, but more so it's probably a combination of 1 and 3 if 3 actually is involved. And that's simply because they theorized that, well, maybe it's so infrequent because it's binding to all of like the dimers I mentioned, which would be a combination of 1 and 3 because 1 was the proteins binding together, forming a large aggregate, and 3 is the internal. So that's what they thought that might be the case. But ultimately, the main takeaway from all of this, though, is that they concluded that in order to have a more definite answer about how these receptors are staying together and staying immobile, then they would need they would need to do further experimentation on the composition of the meshwork, and instead this meshwork is interconnected with the cytoskeleton, because if they had that, then they could better rule out mechanism 3, and then most likely by that case it would probably have been mechanism 2, not mechanism 1, because that would just make more sense. But that is what they had ultimately had concluded.